Section 6.4 is about the central limit theorem, the basic idea of which is that as your sample size gets larger, the sampling distribution would get closer and closer to a normal distribution. However, I stuck this disclaimer in here because our book only relates this to the distribution of the sample mean. And when you look at the section 6.4 homework, that's all it's about. Every question's about a sample mean. And that's fine. That's actually the tougher one. This does also work for proportions though, which is what this disclaimer is about. The proportion case is simpler because the underlying distribution is always the same. It's always a binomial, right? That's what came up in the last section. It was in section 6.3, where with the proportion, the underlying distribution is always a binomial, but then with the mean, the underlying distribution could be anything. So the mean one is actually tougher. So it's actually probably like if you were going to pick one, that is the one that comes up more often. And I guess if you look at the harder one in isolation, then the easier one should also be doable. All right, so first of all, the basic idea of the central limit theorem is that for any distribution, so notice that this always works, any distribution, that as the sample size increases, the sampling distribution of x bar, which would just be the distribution of values of x bar that you'd have if you had lots and lots of samples where you got an x bar out of every single sample. That's going to approach a normal distribution. So graphically, that means it should look like a bell curve eventually, right, with a big enough sample size. So I intentionally picked one where the original population shape is not symmetric at all. So this first graph right here, so of these four, the one that's in the upper left, that's the original population. If you look at that thing, you go, yeah, that's heavily skewed, right? It's heavily right skewed. It's got this long right tail and a tiny little left tail. So you'd think if anything was going to be difficult as far as the central limit theorem goes, like a difficult underlying distribution to deal with, it would be something like really skewed like this. But then if you start looking at these, like here's a sampling distribution with n equals 10, so with a sample size of 10. So these are all little dots in here, and each one represents a sample mean. So I forget how many I would have used here. Yeah, I either have 1,000 or 5,000 in there. So it's either 1,000 or 5,000 sample means graphed, where it's samples taken out of this population, samples of size 10. And if you look at this, you go, well, this looks better, right? It looks less skewed, but it still looks skewed, right? The right tail over here is clearly longer than the left tail. The right tail definitely stretches out farther. You say, okay, let's go a little bigger. What if n's 25? Well, this looks better, right? The one in the lower left looks better than the one in the upper right as far as looking symmetric, right? But still, you go a little bit skewed, right? This right tail is still a little long compared to the left tail. Okay, fine. What if we go to 60? Looks good, right? If you drew in a best fit curve, it's just a nice bell shape. So yeah, it looks like we get there, even with kind of an extreme original shape. And like in the last section where it came up that we're just going to use the rule of thumb of a sample of size 30 would be big enough to apply the central limit theorem and say that our sampling distribution should be approximately normal. So that's what we're going to do. And this is one where the original shape is so severe that you can see like maybe here going a little bit bigger actually would be the right thing to do, because 25 is pretty close to 30 and you go, yeah, that's close, but that 60 looks way better. But we'll stick with that 30 rule of thumb, because if we're saying approximately normal, you can say, well, yeah, I mean, if you went a little bit bigger than 25, you get something that looks slightly better than this one. It should be close, right? This one would still be better, but with 30, you should be close. All right, so then here's another part where I stuck in a bunch of proportion stuff. If you were going to do this thing right here, which I guess we don't have to worry about it right now, but eventually we might, it's helpful to know how to use the ANS function on your calculator. Otherwise, you have to type the square root and then put p times 1 minus p over n, whatever those numbers are, all in brackets or some kind of grouping symbols. So I guess for the future when we actually need this, if you have a calculator with like a recall function or an ANS, it's ANS if you have a TI. But if you have another brand, it might be called recall or RCL for recall. I forget what brand uses that, but I know there's one that does. But you might want to know what those are. So the ANS or recall function on calculator, just because you might have to eventually compute something that looks like this. So like if you had the square root of 0.21 times 0.79 over 1084. There is a way to do that without a calculator, but it's long. You can do it like with area where you get the square inside the other square, but you have to do it over and over and over again. I wouldn't recommend that. I would recommend the calculator. But anyway, if you look at the general idea here, it's if you have a big enough n, a big enough sample size, notice, I'm going to change colors for a second. Notice that this and this are identical, right? Just one's for p hat and one's for x bar. So it applies to both, the idea of the central limit theorem. You get a big enough n, then the sampling distribution will be approximately normal. So for a mean, we said that's going to be at least 30, that we're going to go with that rule of thumb. For a proportion, it would be where the number of expected successes and failures would both be at least 10. So like n times p and n times 1 minus p. But then beyond that, like, so if we just look at the mean for a second. So okay, fine. You got a big enough n. So you know it's going to be approximately normal. Well, which normal distribution approximates it? Because there are lots of different normal distributions, right? They always have the same shape. They always have the bell shape, but they can be centered in different places. And you can have ones that are really scrawny and tall, and you can have ones that are really stretched out and short, right? So which one? Well, if we can specify the mean and standard deviation, then we know which one. So the mean of the sampling distribution of x bar is mu, which makes sense, right? You would think different samples have different individuals, so you would get variations, right? You're not going to get the same x bar in every single sample, but those are going to be centered around the population mean. Okay, like if you had to pick some number for them to be centered around, that's probably the one everybody would pick, and it's absolutely correct. The standard deviation of the sampling distribution, also called the standard error, is this. This you have to watch out for, actually, because it's very easy, if you're not used to this, to forget to divide by the square root of n. So if you have a question where it asks explicitly for the standard deviation of the sampling distribution, just make sure you remember that. Everybody kind of forgets that early on. I've certainly done it. So I guess just be careful there. Because it feels like it should just be sigma in a way because of how here it's just mu, but it's not. As it turns out, the individual values in the population are going to be more spread out than your sample means are. Which I guess would be reflected here because sigma over the square root of n is going to be less than sigma, right? Because presumably n is bigger than 1, right? Samples of size 1, that doesn't really do anything for you. And then with proportions, the mean of the sampling distribution is p. So all of the p hats, all the sample proportions, that distribution is going to be centered at the population proportion. So at least this is analogous to what's going on up here. And then the standard deviation that you get, it looks like the one for a binomial, kind of, except now n is on the bottom. The reason for that is that it is the one for a binomial divided by n. So then if you divide by n, you're dividing by the square root of n squared, and you end up being able to cancel a little bit. But it's because a binomial is set up for a count instead of a proportion. So if you divide by the sample size, you get this one. But that's where it comes from. Like that's where that root comes from. So it doesn't appear out of thin air. It comes out of the binomial or from the binomial. Okay, notation stuff. I honestly don't really use this notation that much. I just kind of think like if it's, you know, mu is the population mean, and I just remember that that's also the mean of the sampling distribution. But you can use the notation if you want to. There's nothing wrong with it. If it helps to keep things organized, then that's probably a good thing. Then standard deviation of the sampling distribution of x bar. So it'll just be population standard deviation divided by the square root of n. Mean of the sampling distribution of p hat is p. And then standard deviation of the sampling distribution of p hat is that root. Okay, then here we can see where as the sample size increases, a couple of things happen. One is that, and this is supposed to be the big thing, is that the graphs would look more like a normal distribution. And granted, like the ones at the end here, the progression, like where n is 50, they don't look perfect. Part of that is just because the graph is so small that you can't really fit a lot of dots in there. And that's why it says like each dot is 7 observations and each dot is 11. If we had each dot equals 1 observation, we'd probably get a more smoothed out looking shape. But it's not going to be perfect if it's, you know, generated from actual data, right? Like the actual like bell curve is an idealized shape, right? Like it's kind of a theoretical construct. But you get something that resembles it to a large degree, and that's the idea. The other thing that's noticeable is the graphs, like if you look at n equals 10 versus n equals 50 in both of these, the one for n equals 50 is taller and thinner, right? The big thing is that it's thinner. The taller is a consequence of being thinner, but the reason it's thinner is because if you look at this up here, the bigger your n is, then the smaller this expression is, right? Because n's in the denominator, right? It's like the idea of how 1/10 is smaller than 1/2. So if n gets bigger, this expression, the standard deviation of the sampling distribution, which is a measure of spread, gets smaller. And if the measure of spread gets smaller, that means that the values are less spread out. And that's exactly what happens. Like if you look here, like this one, it's from roughly, I guess, 2.5 to 4.5. But then here, it's basically just like a little past 3 to 4, but it's thinner, right? Same thing here. This one's basically going from 2 to 5. But then here, now we're going 2.5 to a little less than 4.5, but roughly that, right? So it's thinner. And then as a consequence, it also ends up being taller. Since if everything's bunched together, up is kind of the only way left to go for where those extra dots are going to show up. The other big thing, and I guess here with the normal, you don't really get the effect, because if you start with the normal distribution, then even with n equals 10, what you're going to get is normal, right? So this is just normal all the way down, so to speak. And then here with the uniform, this is maybe more illustrative because this one doesn't look perfect yet, right? You're starting off with a symmetric distribution, which helps you to get there faster. But this doesn't look perfect yet, although this one looks pretty good. And then if we go down to the U shape, this is another symmetric one. And then you go, well, this doesn't look perfect. It just kind of looks like a mound. But then when we go up to n equals 50, that one looks good, right? That looks like a bell. So with the U shape and the uniform, both of those are symmetric to start off with, so you would get to the bell shape faster than you would, like with that other example on the first page where we started off with something that was heavily skewed, but you wouldn't be there right away. With the normal, you get there immediately. And that's actually what this first note is. If the population's normal, the sampling distribution is going to be normal regardless of the sample size. That's why the one with the sample size of n equals 10 already looks good, right? Because it's already normal. Because the original distribution, the population, was also normal. And then note 2, as the sample size increases, the variation decreases. That just means the graph ends up looking thinner, right? And I guess I didn't draw it on this one, but I could, right? Like this one's basically going from about 1.5 to 5.5. And then here, 2.5 to 4.5, roughly, right? Thinner. So yeah, that's what happens, right? The bigger your sample size, the less variation there's going to be. So if you graph the distribution, it's not going to be as wide because the values aren't going to be as spread out. Okay, next, some actual examples. And there's going to be some stat crunch in this too. Because otherwise, without that, I guess we would need either like a calculator or a table or something. But it's easier to do it with stat crunch, especially because that's what shows up in the homework anyway. All right, so this is kind of tying back to an example from the last section, but suppose commute times to the Douglas campus are normally distributed with a mean of 30 minutes and a standard deviation of 8. Okay, so then what we have here, I guess I can write it up in the corner. The mean, which is mu, that's going to be 30. And then the standard deviation, which would be sigma, is 8. Okay, and then in the picture, so here's my normal curve because it says they're normally distributed. So it's going to be centered at mu, so that means it'll be centered at 30. And then we want the probability that a randomly selected student who commutes to the Douglas campus has a commute time of at least 35 minutes. I want to write this symbolically, so I'm going to say if x is the commute time of, it's a terrible looking M, time, that's better, of a randomly selected student. And what we want is that we want the probability that x is at least 35. So greater than or equal to 35, right? Okay, well, if I draw this, and you don't have to draw the pictures, but I think it helps. At least it helps me just to remember, like, okay, I'm in this tail or I'm in this tail. So 35, I mean, this doesn't have to be perfect, but 35 is bigger than 30, so it should be to the right. So let's say if that's where 35 is, the thing that I'm trying to get is this, right? I'm trying to get 35 and up, so it's this right tail. And then this is where we're going to use StatCrunch. And the probability that x is greater than or equal to 35, we should be able to get pretty quickly. So if we go to StatCrunch, there's StatCrunch. So we want the normal distribution, right? Because it said normally distributed. So if I go to Stat, Calculators, Normal. And then the mean is 30, and the standard deviation is 8. And we wanted the probability that x was at least 35. And there we go, right? Looking at the picture, looks like that matches up with the thing that I drew right there. So, okay, we've got at least 4 places. That's 2660, because you'd have to round that up. So, all right, that probability looks like it's 0.2660. Okay, so there's that first one. All right, well now for a little wrinkle, what if instead of finding the probability that an individual student has a commute time of at least 35 minutes, what if now we have a random sample of 25 students? So this right here, I changed the color for a second, this is going to tell you that n is 25. All right, that's our sample size. And then we want the probability that the sample mean commute time is at least 35 minutes. Okay, so now the thing that's in the picture is not just the regular old population distribution. What this is really is now this is going to be the sampling distribution of x bar. That's what this picture is going to represent. So for the sampling distribution of x bar, what we know, and I should do this in a different color instead of blue, maybe green. We know that the mean is mu, but here that's going to be 30 still. And then the standard deviation is going to be sigma over the square root of n, right? Because now we're talking about a sampling distribution of x bar, so it's sigma over radical n, not just sigma. So that'll be 8 over the square root of 25. So that's 8 over 5, which here would be 1.6. Okay, now I guess I can draw stuff. So we're still going to be centered at 30 because it's still centered at mu. And now the cutoff is still going to be 35, but now the 35 isn't going to be that close to the middle because the standard deviation now is 1.6 instead of 8. So instead of me drawing the 35 here, I'm looking at this and I'm going, that's over 3 standard deviations away, because 3 times 1.6 is going to be 4.8. So the 35 is actually going to be like, it's going to be farther than the way I'm drawing it. But you're going to end up with a tiny little tail. So what's going to happen is that we should get a probability that's really small. So now what we want, so we want the probability that x bar is at least 35. So x bar, not x, because we're looking for the probability that the sample mean is at least 35 minutes, right? So then we're going to use StatCrunch again to get it. So in order to get the probability that x bar is at least 35, okay, well, considering that we already have a lot of this put together, we really just need to change the standard deviation. So now this is 1.6, and it's still the probability that x is at least 35, and now it's tiny. So I guess to 3 significant figures is a lot of times how the homework will ask for one of these if it's some really tiny probability like we got here. I guess that would be 0.00889 to 3 significant figures. So 0.00889. So the probability is really low. And notice the only difference between these 2 questions is that the first one is for an individual value, right? It's just for one person. And the second one is for a sample mean of size 25. And you think, size 25, like as a sample size, that doesn't feel that big. And it's not. But it's big enough to cause a drastic change, right? Like here, because then if you just think about this like as a percent, the way most people think about it, you go, it's like 26.6%. That's a thing that's going to happen pretty frequently, right? Like roughly out of every 4 people, one of them is going to have a commute time that's that long, right? But then here, the chance that you would get a sample mean that was that long is really rare, right? Like this is way, way below 1%. It's less than 1/10 of 1%. It's really low. And that's a thing that you kind of have to get used to, because things like that at first, it's sort of hard to conceive of why that happens. But it's really just mostly, and I guess, you can add more theory into it if you want to, but I think the basic idea is just that when you have a sample mean instead of an individual value, there's just a lot less variation. So then effectively that 35 becomes a lot more extreme than it used to be. It becomes a lot more rare or unusual. And as your sample size gets bigger, the more rare it would get. If we had a random sample of 250 students, then the chance of getting a sample mean of at least 35 is going to be remote. Like the number is extraordinarily tiny. So that's essentially the way that this all kind of works out, is that things that don't feel like they're that far away from each other, because you think 30 minutes, 35 minutes, in the grand scheme of things, like in real life, what's the difference of 5 minutes? And for an individual person, it's like, it happens once in a while that you get one that's that long. You get a commute time that's that long. But then when you're talking about sample means, things that look like little differences can turn out to be like these huge differences, right? And that's kind of what's going on here. Okay, the next example. Assessment records indicate that the value of homes in a small city is right skewed, which is usually the way that it works. Right? Housing is one that's always kind of right skewed, right? Because whatever city you're talking about, there are always a few houses that are going to be insanely expensive, right? So then you end up with a right tail. And that's always the way it goes with housing. So this is sort of a classic example of a thing that's right skewed, real estate. And I mean, if we were going to do like a research project, which, I mean, it's tough to fit that one in an online course, but if we were going to do that, then like I've done them before, where whenever people pick real estate, that's always what they end up with is, And they'll look at their sample data and they'll be like, this looks right skewed. And it's like, well, yeah, they kind of always do with that. But anyway, so it's right skewed. That does factor in, right? So we got our shape right skewed. Then the mean of 140,000, we're going to need this. Standard deviation of 60,000, we're going to need that as well. And then 100 homes, we're going to need that. And so what is this telling us here? Well, that right there is our n, right? That's our sample size, the 100. The standard deviation, that would be sigma. The mean of 140,000, that's a population mean, so that's mu. And then we know the population's right skewed. Okay, first off, what's the shape? So we have the shape, mean, the standard deviation. So the shape, well, we said that as far as the sampling distribution goes, right, because that's what it's talking about, the distribution for the mean value of homes selected, that's like selected in the sample. So it's asking about the distribution of the sample mean, right? So that's that sampling distribution. But our sample size is 100, and that's bigger than 30, right? So n is 100, which is greater than 30. So it's big enough to apply the central limit theorem. So that means that we can say that the shape is approximately normal. And that's the part that you get from the central limit theorem. So I'm just going to put CLT in here for central limit theorem. And we can use that because the sample size is big enough, right? 100, it's above that threshold of 30, so we're good to go with the central limit theorem. Next, the mean, well, that's just mu, and we know that that's 140,000, so not a whole lot of work to do there. And then the standard deviation of the sampling distribution would be sigma over the square root of n. So that's going to be 60,000 for the sigma for the population standard deviation divided by the square root of 100. And that's really 60,000 divided by 10. So that's 6,000. I guess I'll put the comma in. Right, when it's just a single number of thousands, sometimes you put the comma, sometimes you don't. All right, so that's a thing that we can put together, right? And the only part that really comes from the central limit theorem is the shape part. These things, like the mean of the sampling distribution being mu, and then the standard deviation of the sampling distribution being sigma over the square root of n, those would still work even if your sample size wasn't big enough. It's just that then you wouldn't be able to figure any probabilities out if you couldn't apply the central limit theorem, right? If the sample size was too small. So you'd be able to do part of this and then you'd get stuck. But because we would have a big enough sample size, then you could say things like, well, if we wanted the probability of getting a sample mean of at least 150,000 or less than 125,000 and things like that, we can figure them out. Because we can say, central limit theorem, approximately normal. We can do this with a normal distribution, right? That's what you get from having a big enough sample size. All right, so having a big enough sample size, or not having one, is mostly what this example is about. So grocery store receipts show that customer purchases have a skewed distribution. Also, this is one that tends to be right skewed, even though it's not specified. That is the way that this tends to go. So I guess I can kind of diagram this stuff again. Skewed, that matters. The mean of 32, we're going to need the 32. Standard deviation of 20, we're going to need that as well. All right, so could we determine, so for part A, could we determine the probability that the next customer would spend at least $35? Well, no, because that would be using the initial distribution, like the population distribution for a single individual, and we don't know what that is. We just know that it's skewed. There are some skewed distributions that are defined. That's true. But we don't know any at this point, and we don't know which one it would be anyway, right? It doesn't specify, it just says skewed. So I'm just going to say no because we need to know the specific distribution. So no, we would need the specific distribution for that, which we do not have. All we know is skewed, which is not really a big help. All right, then how about the probability the next 10 customers would spend an average of at least $35? Well, we can apply the central limit theorem with a big enough n, but that's not a big enough n. Because we're going to use that rule of thumb of 30 and up is big enough. So 10 is not big enough. So for B, I would say no, because n is too small to apply the central limit theorem. And then what about part C, where instead of a 10, it's a 50? Yes. 50, we're good to go, right? So 50 is greater than 30, it's big enough. So C, we can say yes, because this time n is large enough to apply the central limit theorem. And then C we can actually do, right? So if we say that this down here is going to be the sampling distribution of x bar. So always, if you're going to draw the picture, it's going to be centered at mu, which looks like here that's 32. Then we wanted the probability they spend an average of at least $35. So I kind of have a 35 in 2 spots accidentally. That's weird. But I mean, 35 is bigger than 32, right? So this part doesn't have to look perfect, but maybe there's the 35. And then we're trying to get that, right? So then let's see, what do we know about the sampling distribution? So we know the shape is going to be approximately normal because we had a big enough n to where we could apply the central limit theorem, right? Because n is 50. Then the mean would be mu, which is 32, and then the standard deviation would be sigma over the square root of n, which would be, let's see, sigma up there is 20. So this is 20 over the square root of 50, whatever that is. Let's see, I'm going to cheat and look. 2.8284, okay. There's my standard deviation. And then the thing that we want is we want the probability that the sample mean is at least 35. Okay, so then we can go to StatCrunch, and now our mean was 32. The standard deviation was 2.8284. And then this is the probability we want. So if we compute it to 4 places, it's 0.1444. Okay. So 0.1444. And actually, there's one thing I wanted to check. Could you put the standard deviation in as 20 divided by square root of 50? Like this? Will this actually work? Yes. Okay, good. So the way that I just typed in the standard deviation where I didn't round it, the reason I did that was because I wanted to see if you could do the whole thing without actually using a calculator. And you can, right? Because then that's the calculator part, and now you don't have to use that. I mean, I suppose if you have a calculator with the normal distribution on it, you can use that instead of using StatCrunch. That's absolutely true. But if you're going to use StatCrunch, so like in a test situation, if you had StatCrunch but didn't have a calculator with you, I think you'd still be fine since this works, right? Okay, so then I think we've got one last example in here. So let's see. Yeah, before a referendum on a school budget, a local newspaper polls 400 voters in an attempt to predict whether the budget will pass. Now, notice that there's a thing in here that you would never know in real life, right? Like, you would never know this statement right here, right? Like, you'd never know what the population proportion would actually be. So yeah, this is kind of a manufactured scenario, but it kind of builds up to when you would do it for real. So if you're looking at this and you're thinking, wait a minute, you wouldn't know that part. No, you wouldn't, but just go with it for now. And then the 400, that's our sample size, so that's our n, right? And then, okay, if we're gonna do this, then here, and this is one for a proportion, because I wanted to work one of these in, even though this isn't really covered in this section in our book. But then this would be the sampling distribution of p hat. And so then for the shape, let's see, green. So you have to make sure you have a big enough n. So this is where you get your p from, right? So then p is going to be 0.52, just that 52% converted into decimal form. So n times p, which is 400 times 0.52, that's 208, and that's big enough, right? Because they've got to be at least 10. That's way bigger. Then n times 1 minus p would be 400 times 0.48. That 4 doesn't look so good. That didn't make it any better. 4. There we go. That's 192. And they're both big enough, right? So we can just say, I guess, that both are greater than or equal to 10. So n is large enough to apply the central limit theorem. Good. So it's a slightly different check when it's a proportion. Instead of just checking and making sure your sample size is at least 30, then you have to check that n times p and n times 1 minus p are both going to be at least 10. Here you could kind of eyeball it and go, yeah, that's 400. The 52 is about a half. So they're both going to be around 200, and that's way bigger than 10. And yeah, sure, that's what happens. The mean of the sampling distribution is just p, the population proportion, which here is 0.52. And then the standard deviation would be the square root of p times 1 minus p over n, which would be the square root of 0.52 times 0.48 over 400, which is about 0.0250 to 4 places. And then what are we trying to get? So we know the mean of the sampling distribution is 0.52. And then defeat, assuming that there are only 2 options, which it should be. Like if it's a referendum on a budget, it's either going to be yes, I support it, or no, I don't. So defeat would be if they end up with less than half, or even if you say that they don't get a majority, right? Maybe it's got to be a majority, and an exact 0.5 doesn't work. But it's okay either way, because this is a continuous distribution, and there's no difference between a less than and a less than or equal to. So the 0.5 is maybe, it's over here somewhere. So maybe there's 0.5, and we're trying to get this. We're trying to get this tail over here. And I think that tail is actually bigger than the way that I drew it. But so the probability of predicting defeat would be the probability of getting a p hat less than 0.5. I guess less than or equal to, either way. And then we'll have to go to StatCrunch to get it. Okay, so let's see. Our mean is 0.52. and we said that our standard deviation was 0.0250. I think you could probably also do it as the square root of, and then in grouping symbols, 0.2 times 0.48 divided by 400 if you wanted. And then we want the probability that x is less than or equal to, it still says x, but just think in your mind that that's really a p hat. 0.5 goes there, compute, and there we go, 2119 to 4 places. Okay, so yeah, see, I drew it too small. That tail should be way bigger, right? My tail is puny by comparison, but we're supposed to end up with 0.2119. So if 52% of the population actually supports the school budget, the chance that the newspaper would predict defeat anyway is still about 21%. Based on whatever sample they get of size 400. Okay, I think that would cover 6.4. So a lot of it is still using StatCrunch, but the big thing to watch out for isn't making sure you have a big enough n. That's a thing that is fairly easy to remember, that 30 and up, you're good to go. The thing to watch out for is that standard deviation of the sampling distribution where you have to divide by the square root of n. That's an easy thing to forget about. So just be careful with that, be vigilant with that, because that's a mistake that everybody makes at some point.